Hello everyone, welcome to my presentation today. My name is Bharat. I am a PhD student at Northern Illinois University where I work with Michael Papka and Maoyuan. I'm really excited to share our survey on dynamic multivariate networks through the state-of-the-art report. I would like to start my talk with an introduction to the terms in my title. Let us start with multivariate networks. So, what is a multivariate network? When we talk about networks, oftentimes we think about the nodes and relationships between them. But in reality, a network is also associated with many attributes on nodes and edges. These attributes can be of different types as well. We call such networks as multivariate networks. So a multivariate network has two important components: network topology, which is nothing but the structure of the network, and attributes on both nodes and edges. So what is a dynamic multivariate network? Nothing in this world is static and everything evolves with time, and that applies to our networks as well. This is the same multivariate network that we saw earlier. Let's say this represents a small team of non-collocated members working on a project in 2019. By 2020, we can see few changes happen to the network structure. For example, one member left the team and a new one joined the team. Again, by 2021, we can see the changes in both structure and the attributes of network. We call such evolving networks as dynamic multivariate networks. So to define, a dynamic multivariate network is made of three important components, two of which are same as multivariate networks, that is network topology and attributes on nodes and edges. But the third component is changes in both the topology and the attributes of network. These dynamic multivariate networks are one of the closest forms of real-world networks, as many of the real-world networks have attributes and they do evolve with time. Now that I have introduced what a dynamic multivariate network is, here is the outline of the rest of my talk. I'll start with motivation and talk about why we focus on dynamic multivariate networks. Then I'll briefly talk about the background in networks, especially focusing on the visualization aspect of it. And then I'll introduce you to the typical tasks that we perform using dynamic multivariate networks. After that, I'll go into the details of the taxonomy that we proposed. And finally, I'll conclude my talk with our observations on what techniques work better in which scenarios, a sort of summarized guidelines and recommendations. Networks are one of the important data structures mainly because of their ability to model real-world scenarios across a variety of application domains. Here, I'll talk about some of the common applications from three different domains, and those are social networks, physical and life sciences, and software engineering. First, social networks. Across many industries, understanding how communities are forming and evolving with time is a very important task. It has many different usage scenarios ranging from grouping customers based on their shopping patterns to social behaviors. If we move towards academic side, analyzing the evolution of collaborations among researchers has been an interesting area of study. Not just collaboration patterns, many different variants in it, like analyzing citation patterns, and on scientometric side, analyzing similarity and co-occurrence in document collections and their evolution is a major field of study. Moving on to physical and life sciences, this is another vast application area for dynamic multivariate networks. And experiments are very common in this field of research. So a more generic application is understanding the same layout under different experimental conditions. Also, other applications where analyzing changes in interactions is important include evolution of metabolic pathways and protein-protein interactions. Finally, software engineering is another major application area. In fact, visualization of dynamic networks was first used in this field to understand dynamic and complex dependencies among software components. The most common application in this field is understanding software evolution. Typically, a software has multiple releases and versions. Analyzing the dynamics among these versions help us in understanding the history and scale of the development involved. Another application is call graphs. A call graph describes the control flow between components of a program. As programs themselves are dynamic and evolving, understanding dynamics in call graphs helps us in understanding the bottlenecks and thereby improving the software. Now let me give a brief background on networks, especially in the context of visualization. Basically, a network is a mathematical structure. If we look at the mathematical definition of a network, it is a combination of a set of objects called vertices or nodes and a set of relationships between the nodes called edges. A dynamic network is a set of static networks at different points in time. This collection helps us to model the changes in the structure of the network. Now let us apply the same analogy to a multivariate network. First, a multivariate network is like a static network except that it is a combination of three important things. A set of objects called vertices or nodes, a set of sets where ith set represents ith edge attribute values, and a function that returns an attribute vector for a given node. Now, a dynamic multivariate network is simply a set of multivariate networks at different points in time. This collection helps us to model the changes both in the network structure and attributes. A network being a mathematical structure, there is no inherent spatial position associated with nodes to arrange them in an n-dimensional space. But visualization requires a strategy to place nodes at specific positions. In the literature, there are three common approaches to achieve this. Given a set of nodes and edges between the nodes, we can visualize them using node-link diagrams, matrices, or list views. Let us quickly see each of these techniques. In node-link diagrams, nodes are represented using geometrical shapes such as circles and edges using lines or curves. These are one of the oldest visualization techniques. For node-link diagrams, layouts are responsible for assigning spatial position to nodes. Hence, layout is considered the most important aspect of node-link diagrams. Many studies have explored different layout algorithms. Of these, force-directed layouts are the most popular ones. This example here is also created using a force-directed layout. In general, node-link diagrams are very intuitive for network data. They are easily understood by most users, but they suffer from poor visual scalability and clutter. Even with moderate sized networks, we can see a lot of edge crossings and overlappings. Matrix visualizations are used for representing tabular data, but they can also be used with networks through their adjacency matrix representation. Here, nodes are represented by rows and columns, while cells encode edges. Even before the introduction of information visualization as a research field, Jacques Bertin, a well-known French cartographer, used them for various purposes and spent years on refining methods to reorder rows and columns in matrices to clearly highlight patterns present in them. Here is an example from one of his case studies that present how readable the matrix visualization is before and after reordering. Hence, reordering is the most important aspect of matrix visualizations, like the layout is for node-link diagrams. Matrices provide well-organized layout and no visual clutter at all, as there is no chance of edge crossings. Hence, they are ideal for dense and highly connected networks. But on the other hand, matrices are not that intuitive for tracing paths and performing path-related tasks. Also, the complexity of reordering algorithms is a major factor because one has to choose a suitable reordering algorithm out of many that are available based on the dataset and the tasks that they are trying to solve. Hence, there is a bit of learning curve involved in using matrices. Finally, list views. List views are also similar to node-link layouts in the sense that nodes are represented by geometric shapes and edges by lines or curves. But the main difference is instead of depending on a layout algorithm to decide on node placement, nodes are always arranged along parallel axes, as shown in this example. Compared to node-link diagrams and matrices, these are relatively new to the InfoVis community. List views are especially well suited for k-partite networks, where nodes in the network can be partitioned into k disjoint sets and edges always connect nodes from different sets. Here is an example of a bipartite network where nodes are divided into two disjoint sets. As list views look like node link layouts, they are also intuitive and easy to understand, and they also provide an organized layout in contrast to node link diagrams. But they suffer from poor visual scalability, means when the size of network increases, it becomes difficult to give full overview to the user. User must scroll in some direction to have a look at all the nodes in the network. Even though list view representations are available since the days of Venn diagrams, they really became popular as a visualization technique since the design of Jigsaw by Stasko et al. In 2007. Since then, many visual analytics tools started developing visualizations based on list views for sense making of complex data. Now, to give a better understanding of use cases involving dynamic multivariate networks, let us see some typical tasks that we can perform using them. Assume that we are working with a network that models collaborations between researchers in multiple scientific domains. Some of the questions that we might be interested in include: how does collaborations across scientific domains evolve over time? And how different is the evolution of collaborations in any two given domains? And then, how my collaborations or a specific researcher's collaborations across domains are evolving. So if we look at these three tasks, we can see the difference between a regular network task and a dynamic multivariate network task. A typical dynamic multivariate network task relies on topology of the network, attributes on nodes and edges, and the changes in topology and attributes with time. If we relook at these three tasks, we can quickly understand that the collaborations part in the tasks represent network topology, scientific domains part refer to the attributes, and the evolution part refers to the tracking changes in time. If we abstract the tasks and look at what level of network structure each of these tasks operate on, the first task requires us to focus our analysis on the entire network. The second task requires us to focus on specific parts of network like a subnetwork or a cluster. And the third task requires us to focus on an individual node in the network and its relationships. Many task taxonomies are proposed for network data. Specifically for tasks related to evolution, the taxonomies agree that one should support tasks at least three different levels of topology, being global level, group or cluster level, and an individual or ego level. In the paper, we categorize the type of common tasks for dynamic multivariate networks we encountered into three categories, and those are change-oriented tasks, search-oriented tasks, and comparison-oriented tasks. Now, combining these categories with the three levels of granularities of networks that we saw earlier, we have a total of 9 types of tasks, as shown here. In the paper, we also discussed examples for each of these types from the existing literature. Now, moving on to most important section of today's talk, the taxonomy to classify existing dynamic multivariate network visualization techniques. Before going to specific techniques on dynamic multivariate networks, I would like to discuss some of the relevant surveys and state-of-the-art reports. We started our literature review by searching for comprehensive studies available on dynamic multivariate networks and their visualization techniques. Here is the summary of our search results. This first set of references are different studies that focus on dynamic nature of networks. That means they only study how to visualize changes in the network structure. This second set of references are studies that focus on multivariate nature of the networks. Here, the studies only focus on how to encode static networks along with associated attributes on nodes and edges. This final set is the closest set of references that we found which focus on both dynamic and multivariate nature of networks. But they are not comprehensive enough in their coverage of available techniques. So we concluded that no formal taxonomy is available to systematically categorize existing dynamic multivariate network visualization techniques. At this point, we started focusing on proposing a formal taxonomy to classify the existing techniques. And in order to have a comprehensive study, we first started with collecting the corpus. So we have gone through the proceedings of various popular journals and conferences on visualization techniques and applications of network data for the last decade. It resulted in a total of 78 papers, and then we manually went through these papers and filtered them based on the criteria that they should cover both dynamic and multivariate nature of networks. And it resulted in 52 candidate papers, which were then taken for a final step of expansion that involved identifying bidirectional citations. That is, finding relevant publications that are citing these candidate papers as well as the ones that are cited by these candidate papers. This produced a corpus consisting of 104 papers that have combination of novel visualization techniques, applications of existing techniques, and evaluation studies of these techniques. Here we can see the breakdown of the collected corpus by the type of paper and year in which it was published, and this visualization clearly shows the interest in this field of research. If we recall our definition of dynamic multivariate networks, there are three important components that we call as dimensions. So our taxonomy is built on top of encoding techniques used along these three dimensions. The first one is topology encoding. It refers to the encoding of network structure. Here we distinguish between three network visualization techniques that we already saw earlier. Those are node link diagrams, matrix visualizations, and list views. Next is temporal encoding dimension. This dimension refers to the techniques that are used for visualizing temporal changes. Here we distinguish between three categories, and the illustrations are representative of those categories. The first one is single time step category, which represents techniques that focus on presenting only one time step at a time. The second one is multiple time steps category, which represents techniques that present all the time steps together at a time. This is exactly opposite to the single time step category. The third one is embedded timeline. It refers to techniques that weave the timeline into the visualization itself, such that differentiating structure between time steps is very difficult. The third dimension in our taxonomy is attribute encoding dimension, and this is the last one. This one refers to techniques that are used for encoding attributes on networks. Here also we distinguish between three categories. First one is juxtaposed marks, that refers to techniques that use separate juxtaposed view to encode attributes. Second one is nested marks, where the attributes are directly encoded on nodes and edges of the network by making use of their visual channels such as color, size, shape, etc. And the last category is called attribute driven layouts, that refers to the techniques where attribute information is primarily used to drive the layout creation process. Here, the attributes may or may not be visually encoded. Instead, they are used for defining node placement such that nodes with similar attributes are placed close to each other. Now, coming to our taxonomy, we propose a hierarchical taxonomy consisting of three levels. At top level is temporal encoding dimension, followed by topology encoding dimension, followed by attribute encoding dimension. Now, given any dynamic multivariate network visualization technique from our corpus, it can be placed in this three-dimensional space based on the techniques used along each of these three dimensions. Combining what I have presented so far, Here is the complete illustration of the proposed taxonomy for systematically classifying dynamic multivariate network visualization techniques. The intersections where no illustration is provided are the ones where no techniques are available from the existing literature. Now I'll present the review of our corpus using this taxonomy. Let me start with the first set of techniques, that is single time step category. This set of techniques map time information in the data to time in the visualization. Typically, these techniques start with presenting the network at one time step and gradually update the network to future time steps. To present the changes across time steps, animation-based techniques are heavily employed. There are two common navigation approaches used in this category. Those are automated and interactive navigation. Automated navigation offers basic controls such as moving only one time step at a time, whereas interactive navigation offers fine control by allowing users to quickly jump to a specific time step of interest. Another important aspect of this category of techniques is there is a high chance of putting cognitive load on users. That is, when transitioning between time steps, if the changes are not minimal or the animation is not carefully designed, it would be difficult for the users to follow, and it puts a lot of extra burden on them to remember things. Hence, designers spent a lot of effort on researching methods to preserve the user's mental map during the transitions. Some of the techniques employed include preserving node positions across time steps and intelligent use of colors to emphasize the changes gradually. Now, including other two dimensions, we have a total of 4 different subcategories. The first one is juxtaposed node link diagrams. It allows multiple views to encode network structure and attributes. In the examples here from the literature, we can see the juxtaposed views representing only one time step at any given point of time. Coming to nested node link diagrams, we can see the attributes are now encoded on nodes and edges. In practical scenarios, this subcategory limits number of attributes that we can encode because one must focus on changes during the transitions, and it already adds to the cognitive load on the users. On top of this, having complex encodings require users to remember even more, and it is practically not feasible. Animating matrices was never thought of as a possible solution until the animatrix. It's proposed by Raffiangi and Melancon. They studied dynamics in software evolution using staged transitions in matrices. Transitions in cells represent relationship dynamics, and transitions on row and column headers represent dynamics in node attributes. List views are also never used in this category until very recently. In chemograph, nested marks are designed to encode various numerical attributes and chemical structure on nodes, while user actions trigger the animations to present dynamics in the network resulting from the performed action. Coming to pros and cons of this category, due to their heavy reliance on animations, they provide pleasing and eye-catching presentations for storytelling. But they pose hard problems, especially when applied to large real-world networks in preserving users' mental map of the visualization, and requires extreme care during the design. And a fun fact here is majority of the early works and dynamic multivariate networks are dominated by this animation-based techniques. Now let us move to second set, that is multiple time steps category. In contrast to previous set of techniques, here the time in the data is mapped to space in the visualization. Hence, this category of techniques is good at providing overviews of the data as well as comparison of time steps. Also, because multiple time steps are presented simultaneously, existing techniques explore different types of arrangement of these time steps. We summarize them into 4 groups. Those are small multiples, radial arrangement, integrated views, and using a new dimension for organizing time steps. And showing all time steps simultaneously in a static image has an important advantage that it can support analysis workflows. Now, including other 2 dimensions, we have 7 different subcategories in total. The common theme in this category of techniques is the limited availability of space for encoding each time step, as the total available space is divided equally among all the time steps. Now, coming to the first category, that is juxtaposed node-link diagrams. In this case, attribute information is encoded in a juxtaposed view by making use of available compact visualization techniques. In the examples here, we can see pixel displays and parallel coordinate plots are employed to visualize the temporal changes in attributes. This is to mitigate the issue with the availability of limited space. In nested node-link diagrams, existing approaches again can be classified into 2 subgroups. One that uses visual channels to encode attributes and the other that uses complex glyphs or markers to encode diverse set of attributes. In the examples here, we can see first one uses the basic visual channels such as color, size and shape to encode few attributes on the nodes, and the time steps are arranged along a 3rd dimension. And the second example uses a complex marker that is designed to encode more attributes on nodes. In the next subcategory, attributes and structure similarities are used to determine the node positions such that nodes in a cluster are closely connected as well as they have similar attributes. In the examples here, the first one is a novel algorithm to place nodes based on attribute similarity, while the second uses attribute information for aggregations. In either case, attributes are used mainly for analytical purposes than explicit visual encoding. In juxtaposed matrices, we can see the similar theme as juxtaposed node-link diagrams, that is, depending on complex visualizations to work around the issue of limited space. So here, compact pixel displays are again used for presenting temporal changes both in structure and attributes. In nested matrices, along with small multiples arrangement of matrices, more compact arrangements such as radial are also studied in the literature. The example here is time radar trees, where temporal changes are encoded using concentric circles. Each inner circle encodes edge attributes of incoming edges, and the thumbnail at the outermost circle encodes outgoing edge attributes. This single image here encodes a total of 14 time steps. And the second example is again a kind of small multiples view, but also supports additional encodings to identify hierarchical structures and their evolution through integrated flow lines. Moving to juxtaposed list views, we see them as primary choice of visualization for egocentric analysis tasks because of their organized layout and flow metaphor to easily understand the timeline, especially when few nodes are present. In nested list views, again we see combination of using visual channels and complex glyph designs to encode different set of attributes. Especially in the second example here, each node is represented as a radar chart encoding 8 different numerical attributes. Now coming to the pros and cons, because these techniques present a static overview of all time steps, they are well suited for performing analysis and exploratory workflows by employing drill downs. They also support comparison of multiple time steps. But visual scalability is a primary issue because available space is typically divided based on time steps, and as the time steps increase, each time step representation gets smaller space to encode rich set of attributes and topology information. Now let us move to the final set of techniques, that is embedded timeline techniques. In contrast to the 2 previous set of techniques, here time in the data is completely woven into the visualization used for the network structure. Hence, the techniques used for presenting timeline are tightly coupled with the topology encoding technique employed. For node link diagrams and list views, we can either encode temporal changes on nodes or edges, while for matrices, we can make use of many different encodings inside the cells. We include some common examples that we found in the existing literature in our corpus. Now, including other two dimensions, we have 4 different subcategories in total. The first one is nested node link diagrams. The first example here is called Kvyat graph that make use of node-based encodings. Here we can see it applied to visualize evolution of 7 different components of Mozilla web browser across 7 versions and still produce a clear and compact visualization. In the second example, a link segmentation algorithm was introduced to embed temporal changes on edges of the network. The next category is attribute-driven layouts, and the attribute information is used to aggregate entities, and the trend in the evolution is represented on nodes using a line glyph. The next one is nested matrices. We can see matrix cells representing the temporal changes, while cells along the diagonal encode node attributes. The first one here uses bar graphs inside cells, while the second one makes use of gestalt lines to present temporal changes. And the last category is nested list views. Again, we can make use of link segmentation based approaches here, similar to the ones that we saw with the node link diagrams. The example that is shown here is called time-aligned edge plots, where the link segmentation based algorithm is applied on the edges present in the network. Now, coming to the pros and cons, this set of techniques are helpful in generating one of the most compact visualizations and hence is a good choice for presenting overviews as well. On the other side, these techniques are not ideal for networks with more number and diverse types of attributes, as the visualization can quickly become overwhelming for the user to read and understand it. To help our readers interactively browse the taxonomy, we have created a companion website. The website gives brief descriptions to the dimensions in our taxonomy along with the categories in each dimension. Readers can also filter the categories and thereby corresponding publications in our corpus that are of interest to them. Now, moving to the last segment of my talk, that is our observations from the study as guidelines or recommendations to the designers. This visualization here summarizes our corpus using our taxonomy. You can see number of publications at the intersection of techniques along the 3 dimensions in our taxonomy. We can also see multiple time steps with nested marks using either node link or list views remains to be the popular choice among the community. But selection of a suitable visualization technique depends on the analysis task at hand. Hence, to help practitioners, we identified merits and demerits of categories along each of the dimensions in our taxonomy. Here you can see the merits and demerits of the categories in the temporal dimension, topology dimension, and finally attribute dimension. Please refer to our paper for more detailed descriptions and discussions on these tables. Along with the recommendations, we also identified several challenges and future directions for research. First is visual scalability. Scalability is one of the most important challenges of dynamic multivariate network visualizations. Researchers did work on designing sophisticated graph layouts like distributed graphs and layouts tailored to large displays, but they are done only in the context of static graphs and they need to be extended to dynamic realm. Second is attribute dimensionality. Existing techniques can encode only a few attributes, but there are many domain-specific datasets that have hundreds of attributes. So another major challenge and a future direction is to design novel techniques that can correlate structure with a greater number of attributes while capturing dynamics in them. The third one is interaction design. Interaction is such a pervasive element in visualizations. Existing techniques are simply applying available interactions of static networks to dynamic networks, and those interactions focus only on one dimension at a time. But for dynamic multivariate networks, we need to research on novel interactions that help in working with multiple dimensions simultaneously. Finally, evaluation studies. There are many evaluation studies conducted in the space of static network visualizations. But for multivariate and dynamic multivariate networks, there are only a limited number of studies available to provide empirical guidance on which technique to use in what scenario. We believe this is another direction. We need more comparative evaluation studies for dynamic multivariate networks. With this, I want to conclude my talk. We believe our report helps visualization practitioners in choosing techniques that address their analysis needs and researchers to identify gaps and future directions. For those who are interested in learning more regarding our survey, please read our paper or refer to our website. Thank you everyone for attending this talk.